Okay, so here's another example. This one says the area of a square is a function of its side length. So the graph of an area function is different from the graph of a perimeter function. So think about the perimeter function that we just did, where we got a straight line for a graph. Okay, we'll see what happens when we make an area one. For the function area equals side squared, because that's how we find the area of a square, is area equals side squared. We take a side times itself to find the area of a square. It says describe the rule with words and make a table that shows at least 4 pairs of numbers that satisfy the function. Then graph the SA pairs and predict the graph of other points for the function. So first thing we need to do is describe the rule in words. Okay, so our rule is the area of a square equals the length of a side times itself. Okay, that is what this function is telling us. The area of a square equals the length of a side times itself, or side squared. Okay, now it says we're going to make a table that shows at least 4 pairs of numbers that satisfy the function. So we're going to use the same numbers we used on the last one, because again, we can't use negative numbers for a side length. I can't have a side that's negative 1 centimeters, and it doesn't make sense to use 0, so we'll just use 1, 2, 3, and 4. And we're going to do our table the same way we did the last time. So we're going to put the area is equal to our input squared. So our area is equal to 1 squared, which is 1. And so our ordered pair, our input was 1, and our output was 1. So what that's telling us is a square that has a length of 1 for a side has an area of 1 also. So if the length is 1 centimeter, then the area is 1 centimeter squared. So now I'm going to plug in area equals 2 squared. Well, 2 squared means 2 times itself, which is 4. So if I have an input of 2, my output is 4. Then area equals, this time, 3 squared, which is 9. So if we put in 3, we get out 9. And the last one, area equals 4 squared. 4 squared is 16. So if we put in 4, we get out 16. Okay? So there's our input-output table. Now it says we're going to graph these pairs that we got and predict the graph of other points for the function. Okay? So let's go ahead, we're going to do that part on the next slide. Okay, so when we graph these, again, if you notice, we're going to have our output, or sorry, our input, our S scale over here, and our output, our A scale over here. Okay, again, those correspond with X's and Y's. Okay, so our X is always side to side, our input's always side to side, and our outputs, our Y is always up and down. So now when we plot these ordered pairs, we need to look at the S numbers, okay, 1, 2, 3, and 4. That means that I'm going to have enough room here because to count by 1, so I can just go 1, 2, 3, 4, so I really don't need to label this axis at all. But here, the A values go up to 16, so if I count 1, 2, 3, 4 all the way up, I get to 10. Okay, so I can't number this by 1, so I have to number it by 2's. So I should label what I'm numbering it by, so 2, 4, 6, 8, 10, 12, 14, 16, 18, and 20. Okay, because each line is going to count for more than 1. So if that happens, if each line is going to count for something different than just 1, you need to make sure you label what it is. Okay, I'm not going to label this side because these all count by 1's. If that means this side count by 2's, I'm going to label it. Then I'm going to put my points, 1, 1. Well, if I go over 1 and up 1, this time up 1 is going to be just halfway in between the line. Okay, let me get that a little better here. Okay, and then 2, 4 is over 2 and up 4. Well, if I go up 4, that means I'm just counting up 2 lines this time because of my scale. And then 3, 9 would be in between the 8 and the 10. And then 4, 16 would be all the way up here. So if you look, a straight line's not going to connect these. It's going to need to be a curved line. So I'm not going to use a straight edge. I'm just going to go ahead and start and curve my line up. Okay, connect the dots as best I can with the curve and put an arrow on the end of it. Alright, so if that kept going, some more points would be like 5 and 25, which would be way up here. Or 6 and 36 would be up higher, and this graph's going to go upwards pretty quickly. Okay, let's go on to the next example. And we're on to example 3. Example 3 says Xavier and Yolanda are playing a game. When Xavier says a number, Yolanda performs an operation with Xavier's number and says the result. The table shows 4 numbers Xavier said and Yolanda's replies. Describe the rule Yolanda uses and write the rule as an equation. So what we need to do on an example like this is look at how we get from our inputs to our outputs. Okay? Well, how do we get from 2 to 4? And how do we get from 3 to 5? Okay, and it should be consistent each time. Well, I know there's 2 different ways that I can get from 2 to 4. I can either add 2 or I can multiply by 2. Okay? Well, the next one, from 3 to 5, the only way I can get from 3 to 5 is to add 2. And from 4 to 6, again, I would add 2. And from 5 to 7, I would add 2. So, this rule, times 2, is out, because it's got to be consistent between each input and output. So my rule every time is that to get from the input to the output, I'm adding 2. And again, I'm adding 2, and adding 2. So in words, it says describe the rule. Yolanda adds 2 to Xavier's number. Okay? So she adds 2 to Xavier's number, and that gives her the number that she comes up with. So, Xavier's number are x's, and Yolanda's numbers are y's. Okay, so we can say that Yolanda's number is equal to Xavier's number plus 2. Alright? So to write the rule for this, we need to use this in terms of our variables they gave us. So y is Yolanda's number, okay, because that's our output. So instead of Yolanda's name, I'm going to put y. I'm going to put equal. Instead of Xavier's number, because he's our input, they gave us x for that, so we're going to put x. And then we're going to keep plus 2. So Yolanda's number equals Xavier's number plus 2. And this is our rule as an equation, okay, with 2 variables, an input and an output. So I could pick a different number for Xavier's. Okay, let's say I kept this table going, I picked 6 here. Well, 6 plus 2 should give me Yolanda's number, which is 8. If I pick 7 for Xavier's number, 7 plus 2 means Yolanda should get 9, and so on. Okay, so that's how to take input-output tables and write a rule out of it as an equation. Okay, let's go on to the next example. Okay, then our last example, we got some more steps again. This one just says to graph the function y equals 1/2 times x minus 2. Okay, steps on a problem like this are the same as the last time, these down here, except now we're saying we're going to change subtraction to addition first. Alright, so the first thing we need to do is change our subtraction to addition. So again, we circle the number we're taking away, and we're going to put y equals 1/2 x. Minus goes to a plus, and 2 goes to negative 2. So this right here is the function that I'm going to plug into my input-output table, not the first one. I want the one that I changed to addition. So we've got y equals 1/2 x plus negative 2. So there's step 1 done. Now we're going to use these same 5 inputs we had before. So we're going to have negative 2, negative 1, 0, 1, and 2. Now there's a little more to plug in here. I'm trying to figure out my y, so I want to put y equals. I've got 1/2 times my input, which in this case is negative 2, but then I need to add negative 2 to that. Okay, well, order of operations says I always do times first, so 1/2 of negative 2 is negative 1, and then negative 1 plus negative 2 is negative 3. So my input was negative 2, and my output was negative 3. Now I'm going to plug in negative 1, so I get y equals 1/2 times negative 1 plus negative 2 again. Again, the reason why it's plus negative 2 is because that's what this says. Notice the only thing that's changing, my y's stay the same, my 1/2 stay the same, it's my x's or my inputs that are changing each time. Everything else stays. Well, 1/2 of negative 1 is negative 1/2, and negative 1/2 plus negative 2 is negative 2.5. So for an input of negative 1, I get negative 2.5 out. Now notice, Mr. Ayers is doing this math right here in his head, okay, just because there's no space for me to write it down. If you have space and you need to do the math on paper, then do that. So you could show me that 1/2 times -2 is -1, and then -1 plus -2 is how I got, -3. Okay, same thing. I could write 1/2 times -1, which is -1/2, plus -2. When they're both the same sign, negative and negative, I add the numbers. 2 plus 1/2 is 2.5, so it's -2.5. Okay, but again, I'm just not showing that because I really don't have a whole lot of room. So next line, y equals 1/2 times 0 plus -2. Well, 1/2 times 0 is 0. 0 plus -2 is -2. So input of 0, output of -2. Okay, then next line, y equals 1/2 times 1, because that's our input, plus -2. Well, 1/2 of 1 is 1/2, and 1/2 plus -2 is -1.5. So an input of 1 gives me an output of -1.5. And the last one, y equals 1/2 times 2 plus -2. Well, 1/2 of 2 is 1, and 1 plus -2 is -1. So 2, -1 is my last ordered pair. Now notice what happens here. If you look, when we have functions, these numbers should count by the same thing each time. So from -3 to -2.5, I go up 1/2. Then from -2.5 to -2, I go up 1/2 again. And I go up 1/2 here, and up 1/2 here. Okay? So that should always hold true on these function tables. There should be some sort of pattern to get between each one of these numbers. Alright, and the last thing we're going to do, and actually, last thing we're going to do is on the next slide, we're going to take these and graph them. Okay, so let's go ahead and do that over on the next slide. Alright, so to graph this, again, notice if we counted by ones every time, we would never run out of space. And our numbers are small enough that actually we wouldn't run out of space if we counted by 1/2, okay, on each line. And the reason we might want to do that is because we have halves involved here. Okay, so on this one, again, it's okay to label your axis as whatever you want to. So on this one, I'm going to count by 1/2 just because I got halves that I'm dealing with. Okay, so this one is going to be 1/2, which makes this one 1, and then 1.5, and so on. Okay, so actually, because I don't have room on here, and it's going to be kind of hard for me to show this. Okay, I'm just going to write that my axes are counted by 1/2. Okay, so axis count by 1/2. And again, normally if I had room, I would label 1/2 here, 1 here, 1.5, 2, and so on, and show that I'm counting by halves. Because I don't, and my pen's too big, I'm going to go ahead and just put here the axis count by 1/2. So for my x value, my first one, I have to go backwards too. Well, if I go backwards 1/2 and 1 and 1.5 and 2, that puts me right here. Then down 3, I go down 1/2, down 1, down 1.5, down 2, down 2.5, down 3. That puts me all the way down here. Okay, so that puts me about right here for that one. Same thing for the next one. If I go backwards 1, here's 1/2, and then 1, and then I go down 2.5, down 1/2, 1, 1.5, 2, 2.5, puts me right there. Okay, 0, -2. We go to 0, and then -2 will be right here if we count by halves. And then 1, -1.5 will be here. And then 2, -1 will be right here. Whoops, sorry. Missed that spot. Okay, 2, -1 will be right here. So again, still forms a straight line. We connect them. Again, you use a straight edge. I am not, just because I don't have one on my iPad here. With arrows on both sides, and there's my line for my graph. Okay. Now you could have done these axes by counting by 1. Again, then you would just need to put your dots in the middle of your lines, but that's possible. Okay, I know that's a long video, but there's a lot of important information there, so make sure you take your time and ask questions if you need them. Good luck on your homework.